Morning, everyone. Hey, Katie. Hey, Elizabeth. Hey, Carrie. Carrie, did you get my email? Okay, cool. Hey, Kayla. So first thing is to remind everybody that you do have a test. Test one is currently open. It opened yesterday at 5 a.m. Don't worry, it closes at midnight tonight. So you have more than enough time to get that done. So if you haven't taken it yet, make sure you take it. Okay. It is open note, open book. Make sure you study before you take it though, because there is a time constraint on it. Where is the test? You will find it on Moodle. So just go to the Moodle page. I'll share, actually, why not just share the screen so we can chat? We'll go to the Moodle page, and right here will be test one. You'll click on it and it'll open up, and then you can access the test. One second, just make sure I have my computer plugged in here. I want it to die. Yeah, so you have an hour and 30 minutes, which I think is a reasonable amount of time for that first test if you've done some studying, okay? If you are clueless and you're trying to teach yourself while you're taking it, that might feel a little tight. So just review. Yeah, that's the main thing that I want to make sure you're getting done. If you're having any confusion on labs and things like that, feel free to email me. In general, it's usually easier to email and then set up a Zoom meeting so we can talk one-on-one. I just find, unless it's a very like specific question, like, hey, I've got, how is this the right answer, right? And you've already done the calculation. That usually works well through email. But if you have something like, hey, I don't get the whole last page, when you send me an email, just give me some availability on like a Zoom time that would work for you, because I just find that always, we can clear it up much faster that way than through email. All right, so even though you may not have taken test one yet, we're going to move into chapter 5, test 2 stuff. If there was a chapter that you were to say, what is the most important chapter of the semester? This would be it. Okay, chapter 5 is all about compounds and nomenclature. And nomenclature is just a fancy way of saying that you have a naming system. So how do you name compounds? If you can't name compounds, if you can't identify compounds and what's in them, it makes the rest of the semester much, much more difficult. It's kind of like trying to write poetry if you don't know the alphabet, okay? Or you don't know a basic set of words. So you want to get this, all right? And I'm going to try and, I don't want to say dumb it down, but I'm going to try and simplify it as much as I can for you guys and do as much practice problems as we can so that by the end of this chapter, hopefully you're like, yeah, no, I got it. So chapter 5, where are you? Molecules and compounds. We still got people popping in. And the lab for chapter 5 is a like full dry lab. All it is just an endless amount, not endless, but it's a lot of practice on nomenclature. So I think that's a really great lab. Make sure you get it done to really get this idea down. The computer is moving so slow this morning. Issues. Okay, so chapter 5 on molecules and compounds. How are molecules and compounds different than elements? Elements are made up of a single type of atom. Molecules and compounds will be two or more types of atoms combined together in a very specified ratio. So for instance, water here, hydrogen, specifically 2 hydrogens, so H2 and then an oxygen O fused together. Here is what the molecule for sugar is, or sucrose, table sugar. It's a combination of carbons, hydrogens, and oxygens. This is known as an organic material. Organic is that it contains carbon, and then usually it has hydrogen and oxygen in some capacity. We aren't going to be doing any sort of naming with these. So if this looks very scary, we're not talking about organic naming. We're going to stay away from organic naming. If you go into 130 or organic chemistry, you will have to know how to name these things, but we're going to keep it a little more simple than that. But the important thing with this is that the components of it, so carbon, hydrogen, and oxygen have their own properties. Oxygen being in the air, hydrogen, hydrogen gas, which is highly flammable. And then you have carbon. This pencil here, the tip of this pencil is made out of what's called graphite. Graphite is pure carbon, all right? Properties of graphite, totally different than the properties of sugar. So these elements, when they're by themselves, they can actually be quite hazardous, but then you mix them together and then they actually become something that's enjoyable, right? That you'd want to eat, sugar. Here's another example. So I've got sodium, which is just the elemental sodium. So that's Na. So if you look at your periodic chart, that would be number 11 on your periodic chart. And then over here, I have chlorine. Chlorine being number what, 17? Yeah, 17. Chlorine is a yellowish gas. It's very reactive and poisonous. Sodium is a metal, relatively soft metal that is highly reactive with oxygen or air. Okay, both of these things are, they appear pretty inedible, right? Well, when they bond together, you get this thing, which is sodium chloride, or that's table salt. So two things that had indigestible properties has now become something that we season our food with. So great example of how the compound has different properties as the elements that it's made of. But know that anytime you have a compound, you can always break it down into its simpler substances through some sort of chemical reaction. So a couple of the substances that you encounter in everyday life are elemental. But usually the things that you're interacting with, the matter that you're dealing with on an everyday basis is a compound. Why? Because elements in general tend to be unstable. And so they like to bond together with other things to create a more stable configuration. It's kind of like people, not all people, but a lot of people tend to be less stable when they're by themselves, and they are more stable when they're in a relationship or they're in some sort of community, right? So when they come together, create stability. So you do see occasionally free atoms in nature, but even if you have like a gold ring, like there is still other things in there besides just pure gold. A compound is different than a mixture in that they are fused together, and there is a fixed definite proportion. So that means when you're dealing with sodium chloride, okay, which is table salt, it has to be 1 sodium for every 1 chlorine. We're not going to do 2 sodiums for 5 chlorines. We have a specific recipe for it. A mixture, on the other hand, we can adjust. So a mixture would be like salt water. There's the table salt and there's the water. I could dilute it by adding more water. I could concentrate it by evaporating some of the water or adding more salt. So the mixture, we can change it. So over here, this is another example. I have a balloon that's filled with hydrogen molecules, and we'll talk about why it's paired like this in a second. That's called a diatomic molecule, and we'll talk about that in a minute. So we've got hydrogen and oxygens, but the hydrogen and oxygen isn't fused to each other, right? They just happen to be in the same balloon bag, and they're ping-ponging around. This would be an example of a mixture because I could put more oxygen in here and increase the concentration of oxygen, or I could put more hydrogen in. Now let's look at this balloon over here. This is a water balloon. This is an example of a compound. I have they're both hydrogens and oxygens, but here the hydrogen and oxygen are mixed. Here the hydrogen and oxygen are fused together in a specific recipe. What is that ratio recipe for water? 2 hydrogens, 1 oxygen. It's always going to have that ratio. What if I add more water? It's still going to be 2 hydrogens for every 1 oxygen, right? You're not going to change the proportionality. I can't add more hydrogen or more oxygen and still be considered water. So Joseph Proust formally stated this idea of compounds, or this idea of like fixed proportionality with them. So it's the law of constant composition, which says that all samples of a given compound have the same proportions of their constituent elements. So if I have 1 molecule of water, what's the ratio of hydrogen to oxygen? 2 hydrogens for every 1 oxygen. What if I have a bathtub of water? What's the relationship or ratio? It will still be 2 hydrogens for every 1 water. It doesn't matter how much of it you have, the proportion stays the same. So there is another way we can talk about this with mass ratio. I don't really test you guys on this, so you may see it in the homework, but I'm not really going to test you on it. But let's say we have something like 18 grams of water. Okay, for 18 grams of water, 16 grams will be oxygen and 2 grams will be hydrogen. Just trust me on that. 16 divided by 2 is an 8-to-1 ratio. So the mass for water, for pure water, is always going to be 8 grams of oxygen for every 1 gram of hydrogen. Doesn't matter how big the sample is. All right, 8-to-1. Here's another one, ammonia, which is NH3. If you have a 17-gram sample, 14 grams of nitrogen will always be combined with 3 grams of hydrogen. So it's a 4.7-to-1 ratio. Again, if your sample's really large, it's still going to have that ratio. Okay, but let's get into what's more important here. So chemical formulas. So if it's a compound, you are able to write a chemical formula, and the chemical formula is going to be its ratio. It indicates the elements that are present. So you're never going to write an element in your chemical formula that isn't present, that isn't there. That doesn't make any sense. And then you are going to have to indicate as well how many of each of them you have. So we don't write the name out when we're writing the formula, we write the symbol. So always have your periodic chart available so that you can make sure you're using the correct symbol. So like for instance, sodium is not S, sodium would be Na. Some of those can get a little tricky. So we have the symbol, and then you'll have what's known as a subscript. Superscript tells us about charge. Subscript tells us how many of those given elements we have. And if you're not familiar with superscript and subscript, if I was to draw like a little invisible line right here, anything below this line is called a subscript. Anything above this line is a superscript. So looking at the chemical formula for water, we can see the symbol for hydrogen. There's a little 2 next to it. The 2 tells me that I have 2 hydrogens. That 2 always talks about just the element before it or the set of parentheses before it. And we'll look at that in a minute. And then we write oxygen. Now, if I'm writing the symbol for oxygen, it's inferred that I have an oxygen. I wouldn't put it there not to have it. So I don't need to write the 1 because the symbol is enough to say I've got at least one of them. So here we've got a 2-to-1 ratio, 2 hydrogens for every 1 oxygen. Okay, so symbol for our hydrogen, they've boxed it out in this blue color because the 2 is talking about the hydrogen. It's not talking about the oxygen. Oxygen over here with the inferred 1. So how to represent our compounds. Here are some chemical compounds, NaCl, which is table salt, or we can call it sodium chloride. Sodium chloride would be its nomenclature name or its systematic name. Table salt would be what we call its everyday name. How do you learn everyday names? You just have to memorize them. I'm not testing you on everyday names. I'm going to test you on the systematic names. So when looking at this, this indicates that we have 1 sodium for every 1 chlorine. It's a 1 atom to 1 atom ratio. CO2, which is carbon dioxide, you'll be able to name these by the end of this chapter. We have 1 carbon for every 2 oxygens. Okay, this thing here is not something I would expect you to name, again, because we're not doing organics, but I would want you to be able to tell me how many of each you have. So C12H22O11, which is also known as sucrose or table sugar, its ratio is 12 carbons for every 22 hydrogens and every 11 oxygens. A lot of your organic compounds get really big, really, really clunky. So subscripts are so important. Sometimes later on in the semester, like if we're trying to balance an equation and one side has 1 oxygen and one side has 2 oxygens, and you're like, oh, well, I'll just get rid of the subscript. You know, I'll just say it's CO, or I'll just change the subscript. You cannot change subscripts. If you're talking about CO2, it has to have this formula. Why? Because the change of a subscript changes what the compound is, and it changes all its properties. So let's look at CO and CO2. CO is carbon monoxide. CO2 is carbon dioxide. And you may be thinking, oh, well, it's like so close. It's both carbon, it's both oxygen. They probably behave very similar. No, that is not the case. Carbon monoxide over here is an air pollutant that has extremely adverse effects, health effects on people. You probably have carbon monoxide detectors in your house, right? Next to your carbon or your fire detector. CO2, on the other hand, which has just one additional oxygen, this is a relatively harmless byproduct of people, right? We exhale this and plants inhale it to make oxygen. So, you know, if there's a slightly larger quantity of CO2 in the room, it's not going to do anything. If there's a slightly larger quantity of CO, it can kill you pretty fast. So don't change subscripts. If we're talking about carbon monoxide, there's only one of those. Carbon dioxide, there's 2 of those. And we will talk all about how to do these namings. So when putting things in order, if I look at table salt here, I say that it's NaCl, not ClNa. The system goes name the most metallic element first, and then follow it by the less metallic. So when looking at your periodic chart, what do we consider metallic? Metallic is in the lower left-hand corner. So find Fr, which is number 87. Sometimes we call that Fat Frankie because it's a really big material. That's the most metallic thing that you're going to have on your periodic chart. The least metallic is going to be in the upper right-hand corner by helium neon. All right, so sodium, which is Na, number 11, is much closer to Frankie than chlorine is. Right? You only have to hop down a couple steps to get there. Chlorine, you'd have to move through the whole periodic chart. So we're always going to name metals before nonmetals. If you're looking at a compound that is made of 2 nonmetals, then you want to name the more metal-like element first. So if we look at nitrogen dioxide, NO2, I'm going to name it NO2 as opposed to O2N. And this, I mean, for me at least, this looks better than this does. The reason, because I've seen it written like this so many times, and that may be the same case for you all. It may not be. But look at where nitrogen is on the periodic chart. It's number 7. Look at where oxygen is on the periodic chart. It's 8. Look at your zigzag line. What's closer to the zigzag line? Because the zigzag line is what determines a metal from a nonmetal. The nitrogen is closer to the zigzag line. So we're going to say nitrogen is more metal-like. Within any given column, again, the thing that's closer to the zigzag line will be listed first. So if we look at sulfur and oxygen, sulfur is 1 spot down from oxygen. Again, it's closer to the zigzag line. It's closer to the metals than the oxygen are. Are there exceptions to these rules? Always. There's always an exception. This is sort of the ordering of all the elements. So carbon is the most metal-like, fluorine is the least metal-like. But if you just go with like what's closer to the zigzag line, it'll get you there. One exception is this thing here, OH minus. You would think, okay, hydrogen is closer, so we would say hydrogen and then oxygen. But this is how we write what's known as hydroxide, OH minus. And I'll talk about this ion a little bit later, but just know that that is an exception that you want to put in the correct order, O and then H. All right. So, well, I guess we're going to just talk about that now. So OH minus, this is known as a polyatomic ion, which sounds scarier than it actually is. I'll give you a couple examples of some polyatomic ions. So let's first write it out. Polyatomic ion. So what does poly mean? Poly means many, right? Polygamist, many wives, polytheist, many gods. So polyatomic, atomic, easy, atom. And then ion, if you remember from the last chapter, ion is just a charged thing, right? So it has a charge. So many atoms that are charged. So a polyatomic ion is, you can think of it as like a packet of atoms that have an overall charge. So OH minus, which is known as the hydroxide ion. It's one oxygen and one hydrogen bonded together, and they have an overall minus charge. So we just treat that as like a little packet. What's another polyatomic ion? NO3 minus. This we would classify as nitrate. Okay. Another one, SO4 2 minus. This would be sulfate. So for each hydroxide ion, you have one oxygen and one hydrogen, and you have an overall minus charge. Nitrate, let's look at what we've got here. We've got one nitrogen. How many oxygens do we have in this guy? 3 oxygens, okay, with an overall minus charge. So this minus is sort of applying to the whole packet. SO4 2 minus, that's sulfate, that has 1 sulfur for every 4 oxygens. What's the overall charge? 2 minus. Again, that 2 minus is talking about this whole thing as a packet. So it doesn't just apply to the oxygen, it applies to this whole little nugget. There is a polyatomic ion sheet in the notes, and you can find them online really easily and in your text. I used to make, when we were in person, I would make y'all memorize polyatomic ions, but we're all kind of getting a break for this semester. So looks like we're going to revisit this a little later. But here is a sheet with everyday polyatomic ions. Is this all the polyatomic ions? No, there are hundreds and hundreds. But these are the ones that you'll see most often. So acetate, if you've ever heard of acetate, like or acetic acid or things like that, that'll have this formula. So acetate is 2 carbons with 3 hydrogens and 2 oxygens, and the whole thing has a minus charge. All right. Carbonate, or if you've heard of bicarbonate, these are the different formulas for that. There's hydroxide, our buddy that has the H after the O, nitrate, nitrite, we've got all these things, okay? So have these available. Know that they don't really break apart. In certain chemical reactions, it'll break apart, but for the sake of this class, you're gonna treat this as like a chunk, just like you'd treat sodium. Sodium is Na. You wouldn't separate the N from the A, right? It's a packet. We're gonna do the same thing with these. We're gonna treat them as kind of packets because they're very stable together. Okay, so head back here. So when we're looking at a formula that contains a polyatomic ion, let's say we needed to multiply out the number of polyatomic ions, and we'll get into that a little bit later. But let's look at this thing here, MgNO3 2. I'm gonna write this over here. Okay, so we have MgNO3 2. This is known as magnesium nitrate. And by the end of this chapter, you will be able to name that and write a correct formula for it. So right now, all I want to talk about is how many of each element we have. So let's talk about what elements we see here. So we've got magnesium, Mg. We also have this nitrate, which contains what? We've got a nitrogen and we've got an oxygen, right? I don't see any other elements in there. I want to know how many magnesiums are in here. So let's look at magnesiums right here. I don't see any number as its subscript, so we can assume that it has a value of 1. So we've got 1 magnesium. Let's look at nitrogen. Nitrogen is in this parenthesis, in this like packet, right? So here's nitrogen. In this, I have 1. But do you see how there's a set of parentheses? That's saying I have 2 of these nitrates. So the 2 is going to multiply any subscript within the parentheses. So I take the 2 times the 1 for a total of 2 nitrogens. What about oxygen? Oxygen over here, I have 3 oxygens, but there's 2 of these polyatomics. So I'm going to multiply that by 2. And that'll give me a total of 6. And if you don't believe that you want to multiply, I'm going to draw out a really simplified visual of what this is. So NO3 looks something kind of like this. There's a nitrogen in the center. It's connected to an oxygen, and oxygen, and oxygen. Okay. If I have 2 of them, I have to draw 2 of them, right? So nitrogen, oxygen, oxygen, oxygen. Well, let's count up the nitrogens. So there's 1 here, and there's 1 here for a total of 2. Oxygens, there's 1, 2, 3, 4, 5, 6. 6 of them. Now, I wouldn't really recommend drawing them out every time like that, but that's where this multiplier is coming from. So I'm going to give you another one. I want you to tell me what elements are contained in this thing and how many of each there are. Al2SO4 3. This is known as aluminum sulfate. Don't stress too much about the name right now. I will teach you how to name those. Right now, I just want you to tell me what are the elements that are there and how many of each do you have? Just another 20 seconds or so. Shouldn't take you too long for this. Okay. So we've got, in this one, I've got aluminum, and then this is the sulfate ion. I'm going to break it up into its individual things. So I have aluminum, I have sulfur, and I have oxygen. Aluminum, this subscript is telling me I have 2 of them. So 2 aluminums. Sulfur, I've got 1 sulfur here, right? The subscript of an inferred 1, but there are 3 of these packets. So I'm going to take the 3 times the 1. So this equals the 3 times 1, which should give me a total of 3. Oxygen, I have 4 within the parentheses, but there's a 3 on the outside. So I'm going to multiply by 3 for a total of 12 oxygens. 2, 3, and 12. Not too bad, right? Pretty simple. If they get more complicated with parentheses and stuff like that, you just keep multiplying out. So 1, let's do ammonium nitrate. That would be NH4, 2. Oh. And let's do ammonium carbonate, CO3. This is a polyatomic ion. This is also a polyatomic ion. It's 2 polyatomic ions smushed together. If you ever come across a situation where you're trying to name something and you're like, there's too many atoms, it's really confusing, look at your polyatomic ion sheet because it's probably a polyatomic ion. And this is specifically ammonium carbonate. All right, so what do we have in here? We've got nitrogens, we've got hydrogens, we've got carbons, and we got oxygens. Nitrogen, I have 1 within the parenthesis, but there's a 2, so it's 1 times 2 for a total of 2 nitrogens. Hydrogen, I have 4 within the parentheses, right? But there's 2 of those, so multiply it by 2 for a total of 8. Carbon, just 1. It's not within a parenthesis, so I don't need to multiply by anything. And then oxygen is just a straight up 3. Any questions on that before we move on?
I have a question.
Yeah, what's up, Carrie?
If you have the parentheses around it, and will there always be a 2, or will there sometimes be no 2?
So if I was to take this compound here and combine it with something called nitrate, so NH4 NO3, if I only have one of these things, I'm not going to put it in parentheses like this. Okay, the parentheses will only be written if there's going to be a 2 or a 3 or a 5 or something outside of it. Does that make sense?
Okay, so parentheses themselves don't signify 2. They just
no. The parentheses are just saying, hey, group these together and take the whole thing and multiply it by 2.
Okay, I just wanted to check. Thank you.
Yeah, a lot of times when I see a set of parentheses, I will just sort of like visually like circle it, or I will tell students to sort of circle the parenthesis thing, because the 2 then is applying to that whole thing. There's no parentheses, there's not going to be a subscript to multiply it by. Other questions on that? Great, so let's move on. So when writing a chemical formula, we can write a couple different types of chemical formulas. There's what's known as an empirical formula and then a molecular formula. For you guys, a lot of what you're working with, the empirical and the molecular will actually be the same. But an empirical formula is the relative number of atoms of any element, its lowest ratio. So like, how many carbons do I have for how many oxygens? The molecular formula is what's actually happening in real space. So how many carbons and how many oxygens are there within it, not just its lowest ratio. So a really good example of this is hydrogen peroxide. Hydrogen peroxide has this formula here, H2O2. This would be its molecular formula. There are 2 hydrogens bonded to every 2 oxygens. The empirical formula would be taking this and stripping it down to its lowest ratio. So if I divided each of these by a factor of 2, I would get HO. Again, this happens a lot with organic compounds. When you get these really, really big compounds, you kind of reduce them down. So let me show you another one. So anytime you can reduce it down, it's a molecular formula. Anytime it's non-reducible, you can't divide it out, it's its empirical formula. Say we have, I'm going to make something up, C11H33O22. Okay, would you call this a molecular formula or an empirical formula? Is this reducible? Can you lower its ratio down? Yes. So I'm going to say that this is the molecular formula. Let's find its empirical formula. So, what is the empirical? Well, what can we divide each of these things by? We can divide them all by 11, right? 11, and still have a whole number, okay? You have to be able to reduce it to a whole number. So if I divide each of these by 11, carbon now has a subscript of 1, hydrogen has a subscript of 3, and oxygen has a subscript of 2. This would be the empirical, this would be the molecular. Why would you do that? Because sometimes you just need the lowest ratio, you don't need all the like cumbersome numbers. You don't need to know that there's actually 11 for every 33 for every 22. You only need to know that it's a 1 to 3 to 2 ratio. So be able to find either of those. Something like water. Water is H2O. Can I reduce this down? No. So this is the empirical formula. But this is also its molecular formula. If I was to go into real life and like look at, you know, a water molecule, it isn't like, it's not H4O2. It is, in fact, 2 hydrogens for every 1 oxygen. So there are times where your compound can be its empirical and its molecular. Now, outside of like water, I wouldn't expect you to know what's happening like in real space. So don't get scared about, oh my gosh, I need to memorize every molecular and empirical formula for every formula out there. That's not the case. But something simple like this, I could give you something like this and say, hey, give me the empirical formula, or is this an empirical or molecular or something like that. There are some other ways to represent formulas. Another one is a structural formula. A structural formula gives a visualization to the empirical or molecular. So when I drew that NO3 and I put the little lines, that would be a structural formula. So here's a molecular formula for methane, CH4. Here's a structural formula. We put the carbon in the center and the 4 hydrogens around it. There is a system to this on why the hydrogens are outside and the carbons in the center. You will learn that 2 chapters from now. So don't get too stressed about that. For now, just know that your molecular formula or whatever your written formula is can actually be visualized. Sometimes they're drawn a little bit more detailed in these ball and stick models or these space-filled models. I wouldn't expect you to draw these like 3-dimensional structures. I can't even draw these. We're going to stick with structural formulas in about 2 chapters. All right, so let's take a moment to look back at how we classify matter. So we have matter, and we can say that it's either a pure substance or a mixture. We're going to hang out with pure substances. So a pure substance can be either an element or a compound, right? An element meaning it's made of one thing, a compound being 2 things bonded together. Now we can actually take that a step further. So if you have your flow chart from before, you can break up elements into either what's called atomic or molecular, and we can break our compounds up into either molecular or ionic. So let me give you the visualization here. So here was our pure substances, right? This attaches to matter, and mixtures are somewhere over here. If we're in the pure substance, you've got your elements and you've got your compound. If you're an element, you can be what's called atomic or you can be molecular. Atomic means that you exist as free elements, like neon here. Molecular, sometimes instead of molecular, this is called diatomic. Di means 2. Atomic means atoms. So 2 atoms. So there are certain materials when they're in their elemental form that they like to stick to themselves in a pair. They're called diatomic molecules. Oxygen is one of them. So you're never going to see oxygen by itself. Like if it's in elemental form, you're never going to just see an oxygen by itself. It's always going to bond to a secondary oxygen. So we call it O2. Why does it bond to another oxygen? It is more stable when it's coupled to another oxygen. When it's just a free oxygen element by itself or a free oxygen atom by itself, it's very, very unstable. So what are all the diatomics out there? The diatomic molecules, okay, we got that. Here's, this would be an example of an atomic element, mercury lined up as single atoms. Here is a molecular or a diatomic, chlorine couples together. So here are your diatomics. So on your periodic chart, make note, go to, you're gonna wanna like highlight hydrogen or mark, circle hydrogen. and then hop over to nitrogen, and then you go just across and down. So it's nitrogen, oxygen, fluorine, chlorine, bromine, and iodine. Those are all the elements that exist as diatomics when they're by themselves, not when they're fused to other things, when they're in their elemental form. So nitrogen is never just going to be one nitrogen atom floating around. It's going to be nitrogen fused to itself. One way to remember, have no fear of ice cold beer, but beer is bromine, not boron. Okay. And cold is chlorine, not carbon. So now, if you know your diatomics, it's really easy to figure out what all of your atomic or elemental atoms are, or atomic elements. It's everything else. Okay, so you are never going to see, let's say lithium, number 3. Lithium by itself is never going to form a diatomic. Neither are any of the other metals. Neither is the noble gases. Carbon won't do it. Phosphorus won't do it. Sulfur won't do it. It is only these guys that pair that up. This will come back to bite you in the butt. So know these or have them marked. We don't have any triatomics. Okay, so there's no elements out there that like to exist in a coupling of 3. It's going to be 2 or elemental. Now, a little bit more complicated is how we divide up compounds. So back on this flow chart, if I look at my pure substance and I've decided it is a compound, it's 2 or more elements that are fused together, we can classify it as either molecular or ionic. Sometimes molecular, you may see it called covalent, interchangeable. So what's the difference between these two things? Okay, a molecular compound is going to be a compound formed by 2 or more nonmetals. The basic unit of a molecular compound is a molecule. So sugar is an example. It's carbon, hydrogen, and oxygen. All of those are nonmetals. I can classify it as molecular. Molecular compounds share electrons. We'll talk a little bit about that in a few chapters, but you can just make note that molecular compounds, they like to share the electrons. They form these little molecule packets. Ionic compounds, on the other hand, contain 1 or more cation paired with 1 or more anions. Now, don't get freaked out by cation, anion. Remember, a cation is another name for a metal. Metals form cations. Anion is a nonmetal. So in most cases, ionic compounds are going to be a metal combined with a nonmetal. These transfer electrons. So ionic compounds transfer the electron as opposed to sharing them. Like molecular compounds, you and your buddy are going to share a pool of $500, right? You've got 200, he's got 300, you're going to share it for some sort of investment. An ionic would be you've got 200, he's got 300, and you give him the 200, and he takes all 500 to do whatever it is he's going to do with it investment-wise. So let's look at an example of a molecular versus an ionic. CO2, carbon dioxide, is a molecular. It is made up of, this is dry ice, it's just made up of CO2 molecules like compacted together. So there's these little packets of carbon with 2 oxygens, individual molecule units. That is different from an ionic. An ionic compound, which is NaCl, this is sometimes called its formula unit. It's 1 sodium for every 1 chlorine. There's the sodium and the chlorine, but it is built into this 3-dimensional lattice structure. So this sodium is connected to this chlorine, but it's also connected to the chlorine above it, to the side, below, front, and back. All right, and it makes this 3-dimensional lattice. So a lot of times these ionic compounds are solids, and it forms like a repeating pattern. Versus here, where you have these little individual packets, like this molecule isn't like in a lattice structure with this molecule, it's just sitting next to it. Here, they're all fused together. So it makes these this is a very strong structure. Ionic compounds, very strong structure. It takes a lot to melt them or break that apart. Think about table sugar or table salt rather. If it falls on your stove, the salt doesn't like melt. It just, you can brush it away. Dry ice will melt as soon as you open whatever container it's in. It won't even melt. It'll vaporize. So when looking at an ionic compound, before we even do that, I want you to tell me whether these things are molecular or ionic. It's my daughter. She snuck in. Can you say hi?
Hi.
They're learning chemistry. Yeah.
Chemistry.
What's chemistry? I'll teach you. All right, I gotta go. I gotta work. Go see Brittany. Please close my door. Sorry. Hey, Gabby, please close my door, honey. So let's see, we've got SO3, CaCl2, Na2SO, no, Na2SO4, and C11O12H33. All right, all I want you to do is tell me, is this molecular or is it ionic? And it seems really simple, but this is how you like name everything. This is the starting point. If you can't break those apart, you will name things incorrectly. Okay, so it's really, when deciding if it's molecular or ionic, it's really just looking at that first thing, and is it a metal or a non-metal? Because remember, if we have a metal in our material, we're always going to name the metal first. So this first thing, is it a metal? No. It's two non-metals. Sulfur and oxygen are both non-metals. So non-metal means molecular. This one here, what's that first thing you bump into? Just like if you were reading a book, you read left to right. So the first thing is calcium. Calcium on your periodic chart is in fact a metal. Look at number 20. It's located to the left of the zigzag line. So that is a metal. So we're going to say that this thing is ionic. This one is looking a little bit more complicated, but it still follows the same rule. What's that first thing we bump into? Na. Na is sodium. Sodium is a metal. So we're going to say that this is ionic. This thing here, first thing I bump into is carbon. Carbon is definitely not a metal, but if you don't know that off the top of your head, just look at your periodic chart. Where does it sit? It's number 6. It's to the it's up and to the right of the zigzag line. So that's a non-metal. So we say that this is molecular. You want to be able to do that, because the way that I name this and this is different than the way I'm going to name this and this. They have two separate sets of rules. No, we don't need my email. So what is actually happening here in our ionic compound? We have this metal which tends to lose electrons, combining with a nonmetal, which likes to eat up or gain electrons. When you have something that loses electrons, it forms a cation or a positively charged thing. When you have a nonmetal that takes on the electrons, it forms a negatively charged thing. Well, what does a positive thing and a negative thing like to do? Think about the opposite ends of a magnet. They like to stick together. So by transferring that electron, you've now stuck or fused them together. As far as being ionic, it's going to be a metal with a nonmetal. Now know that your nonmetal could also be a polyatomic ion. Okay, so it could be like NO3 or anything from that list. The basic unit of an ionic compound is known as its formula unit because it's in that three-dimensional lattice structure. And unlike molecular compounds, ionic compounds do not contain individual molecules. So it's not like when I'm talking about sodium chloride, NaCl, it's not like it's an Na and a Cl like floating around as an individual molecule. It's in a three-dimensional lattice structure. So if we're going to write a formula for an ionic compound, first thing we have to do is review the charges of the elements, or the ones that have predictable charges. So ionic compounds like to give up electrons to become some sort of positive magnitude thing. So remember over column 1, where hydrogen, lithium, sodium, potassium, rubidium, what number did you write above there? You wrote a +1, because those things like to give up 1 electron. Okay, so just remember that. Column 2, beryllium, magnesium, calcium, strontium, we put a +2. Hop over the transition metals because they do funky things. Aluminum, gallium, we said got a +3. That doesn't include boron because it's a nonmetal. We're going to skip the carbon, silicon. They can kind of go either way. Nitrogen, the column for nitrogen and phosphorus, what did we put? We put a -3. Oxygen and sulfur, we put a -2. Fluorine, chlorine, bromine, iodine, we put a -1. And then over the noble gas, you put a 0 with a slash through it because they don't form a charge. Those are the predictable charges. The other predictable charges, remember, go to aluminum on your periodic chart. That's a 3+. Go down into the left to zinc. That's a 2+. Go down into the left silver. That's a 1+. Okay, so those are all of our predictable charges. So in a chemical formula for an ionic compound, the sum of the positive charged ion needs to be equal and opposite to the sum of the negative charged ion. So the amount of electrons being given up by the metal has to equal the amount of electrons being taken on by the nonmetal. So how do we do that? Well, you write the symbol for the metal and its charge. Then you write the symbol for the nonmetal and its charge. And then you take the magnitude of each and you flip-flop and make them the subscript. If possible, reduce subscripts. So I think it's easier if we just do an example. So let's do this one here, calcium chloride, because it's already written, and that's how I wrote it. And you may be wondering, well, why is it CaCl2 and not CaCl? So calcium, Ca. First thing I do is write the metal and what is its predictable charge. So calcium always has a 2+ charge. So I'm going to write that in the upper right-hand corner, 2+. Then I'm going to write the nonmetal over here. I'm going to make some space. I'm not like smushing them together yet. I'm just looking at the ions. So chlorine is Cl, and what is its charge? It's a 1-. You might not always see me write it as 1-. You might just see me write it as minus. There's an inferred 1 there. So what we are going to do, because we've got to balance it out, right? The positive charge has to equal the negative charge. So there's a 2+ charge. There's only a 1- charge. So I need 2 of these to balance out 1 of these. Or I take the magnitude, that's the number. I take the number of this and drop it to the subscript of my chlorine. I take the number of this, not the charge, just the number. This is 1, and that becomes the subscript of the other guy. So calcium is going to have a subscript of 1. I take that and drop it down there. Chlorine is going to have a subscript of 2. Right, this comes down here. You have to flip-flop. Let's double check and make sure that the charges actually equal a neutral thing, or it's 0. Calcium has a 2+ charge, right? Let me just write the 2+. So calcium has a 2+. And how many of them do I have in my final formula? I have just one. So what's my overall positive charge? It's a 2+. Chlorine has a 1- charge. How many of them do I have? In my final formula, I have 2 of them. 2 times 1- equals 2-. What happens when I add those together? I get 0. We are, in fact, charge neutral. So anytime calcium and chlorine come together, it's always going to be written in this formula. I would never write CaCl. Why? Because it's not charge neutral. We don't like that. Let's look at some other examples and we'll do some practice. So aluminum and oxygen. If I take aluminum and I want to combine it with oxygen, I take the magnitude of aluminum. Well, first I write the metal out. So aluminum with a 3+ charge always has a predictable charge. Oxygen has a 2- charge. I take the magnitude of the 3 and I stick it down here. I take the 2 and I stick it down here. So Al2O3. If aluminum and oxygen are coming together, this will always be the ratio. Let's double check and make sure that the charges are, in fact, it does create a neutral formula unit. You don't have to check the charges every single time. I'm just doing it to show you guys. So if I have aluminum always has a 3+ charge. 3+. And in my final formula, how many of them do I have? I have 2, so that's an overall 6+ charge. Oxygen has a 2- charge. How many of them do I have in my final formula? 3 for an overall 6-. When I add those two together, what do I get? 0. And you may be thinking, well, I'm just gonna well, obviously if there's 3 here and there's 2 here, you would just flip-flop and find the lowest common denominator. Yeah, you can, however it works for you. This is the fastest way though, is to flip-flop. Let's look at this one over here. If I take magnesium and combine it with oxygen, magnesium has a 2+ charge. And if you're saying, where are you getting these numbers? It is the number you're putting at the top of the column that I told you to write on your formula sheet. So if you're in column 2, where magnesium is, you form a 2+. If you're in column 6, like oxygen is, you're always going to form a 2-. So we flip-flop 2 and 2. This isn't quite done yet, though. I have to reduce it down. So I divide each of these by 2, and my formula would be MgO. This is actually the correct formula for magnesium and oxygen. Any questions on that outside of, obviously, we need to practice? Don't bring the charge down. I see it so often where people will say 2, so they'll start putting a 2- down here. No. Here we're talking about charges. Here we're talking about the number of atoms. The number of atoms won't have a negative value to it or a charge to it. What other things do I see? I see people, instead of flip-flopping, they will, they'll have their aluminum and they'll take the 3, they'll go Al3O2, and they'll just take the 3 down to the aluminum and the 2 down to the oxygen. You have to swap the places, okay? So don't pitfall there. Other things I see, people writing formulas like this, Al with a 2, O3. So they've flip-flopped, but they've kept it in a charge position as opposed to dropping it down into the subscript, which tells you how many atoms there are. So don't do that. So top, this is talking about its charge. Bottom, this is talking about its number of atoms. So this is 2 aluminums. This is 3 oxygens. Those are some things that I see people do quite often. All right, I'm going to give you some to do. Let's have fun. So I'm not going to give you the standard name. I'm just going to say combine these 2 things together. Okay, so combine lithium and sulfur. Combine potassium and bromine. Combine zinc and sulfur. And then I'll give you one more. Combine nickel and phosphorus. I'll give you 3 minutes. Just another 30 seconds to kind of close up your thoughts. Okay, so the first thing you have to make sure that you're dealing with is an ionic compound. So you do want to make sure that this is a metal. This doesn't work for two nonmetals. If I had given you carbon and oxygen, you would not use this flip-flopping. Flip-flopping charge neutrality only applies to ionic stuff. Only metal and nonmetals do this. If we're doing molecular or two nonmetals, we're going to follow a totally different thing. So this is a metal. It has a predictable charge. Lithium, Li, always forms a plus charge. right? Why is that the case? Because it's in column 1, and I've told you to believe me on that. Sulfur always forms a 2- charge. Why? Because it's in column 6 and we put a 2- above it. So you're just gonna trust me on that. So we're gonna flip-flop the magnitude for the subscripts. So lithium needs to get the 2, sulfur will get the 1. So Li2S is our answer for that. I'm not gonna check all the charges for each one of these to make sure I know that this is the right formula. Any questions on that, on where those numbers came from, on why we're doing that? All right, next one, potassium and bromine. So potassium is K, not P. It also has a plus charge. Bromine, which is Br, has a -1 charge. That's a 1-to-1 ratio, right? One of these will balance out one of these. So K, Br should be the formula. Zinc and sulfur. So zinc, Zn, remember, is one that I want you to treat as a predictable charge. We said zinc has a 2+. Sulfur is S, and it has a 2- charge. So when we flip-flop, we get Zn to S2. Not quite done. We want to divide by 2 because we want the lowest common ratio because it's a ionic and it's a repeated lattice structure. So this would end up being ZnS, and we are good to go there. This last one, nickel and phosphorus. I hope that you got stuck here because what is the charge? Is nickel a metal? It is definitely a metal. What's the charge of nickel? I have no idea. Did you write anything above that column? No. Those metals in the middle are called transition metals. They can form different charges. So in this case, phosphorus always has a 3-. Nickel is, I don't know. So we can't write a correct formula for this with just this amount of information. We need a little bit more information, and I'll show you that in a couple slides or maybe next time. But this is wah-wah, we got nothing. Not applicable as of now. Why is that the case? Well, I don't know the charge here, so I don't know how many of these I need to balance out these. If it was 3+, right, we could go nickel and phosphorus. If it was 2+, I'd have to flip-flop for that accordingly, so on and so on. So we don't know what its formula is right now. So outside of this last one being frustrating, are these 3 making sense? Is the flip-flopping making sense? Okay, great. So back to polyatomic ions. So a polyatomic ion is a collection of atoms that has that charge. So that whole flip-flopping thing, we can do with polyatomic ions as well. All right, the only thing is that you've got to take into account like a package. So I'm gonna write over here, we're gonna combine calcium and nitrate. And I'm gonna put in parentheses, this is nitrate, NO3 with a minus charge. Okay, so 1 nitrogen, 3 oxygens, and the whole thing has a minus charge. So when writing a formula for this, calcium, we know is a metal, we know it has a predictable charge. It is gonna be Ca with a 2+ charge. My non-metal in this situation is just nitrate. It's behaving as the non-metal. So I'm gonna flip-flop. Now, when I go about this, circle this so that you treat this as a unit, okay? And leave the charge on the outside. So circle that. We want to keep that grouped together. So when I flip-flop, well, what is this charge over here? It's a -1. So calcium, I should have 1 of those, right? Nitrate, I've got to treat it as a packet. How many nitrates am I going to have? Well, the 2 means I have 2 of these. So how do I write that as 2 nitrates? I put it in parentheses, and then I put a 2 on the outside. You guys see how the 2 is getting dropped here and the 1 is getting dropped there? Some pitfalls that I see here. So these are things you don't want to do. So maybe don't write these down, but I'll get calcium from a student and nitrate, and they're all set up. And they go like this, CaNO3 2. Why don't we like that? We definitely don't have 32 oxygens, okay? So yes, they've dropped the 2, but they haven't put this thing in parentheses and treated it like a packet. Another thing that I see students do, Ca2 plus, NO3 minus, is they flip-flop and they go Ca3NO2. What's happened here is they've taken the 3, which is a subscript, and they've sort of lifted it up or fused it together. And then they've dropped that. And then what is this? This is not nitrate. They changed the subscript. Where did the 3 go? It disappeared. Well, it didn't disappear. They assumed it was a charge and then put it over here. So don't do that. Sometimes I'll see students do Ca2 plus, NO3 minus, flip-flop, and they'll do CaNO3. And they'll just disregard the 2 because it's like, gets too cumbersome and they get freaked out and they won't put it down there. You got to bring it down just like you would a metal and a simple non-metal. So I'm going to give you one. All right. And I'm going to have you look up the polyatomic ion. So you can look up on your phones, whatever sulfate ion. So let's take aluminum and we're going to combine it with sulfate. And I want you to write me the correct formula. And I'm going to give you like 60 seconds because we're almost done with class. All right, I'm going to run through this just so that we can honor time. So aluminum is a metal with a 3+ charge. I know that I can do what I'm doing here. Sulfate is a polyatomic ion. It is called SO4 and it has a 2- charge. You would get that off a polyatomic ion sheet. So we want to treat this thing as a packet. Circle it if you like. We're going to flip-flop. So aluminum is going to take the 2. We drop the 2. Sulfate is going to take the 3. So I need to put sulfate in parentheses and then bring the 3 down. If you get a situation, just real quick, if I have something like sodium, which is a plus charge, and nitrate, NO3-, sodium and nitrate. Flip-flop. Sodium, I'm going to have one of them. Nitrate, I'm also going to have one of them. So I don't put it in parentheses like this. I ditch the parentheses. All I have to do is write the formula. Okay. If you only have one of them, don't use parentheses. Only use the parentheses if you've got to multiply it by a factor of 2, 3, 4, whatever. Okay. So that's where we'll stop today. We'll do a little bit more practice with this before we move on next time, just to refresh. There's a couple people that I know have questions through emails and stuff, so stay around. Otherwise, enjoy your day. Don't forget to do your test. It is due tonight by midnight, so get that done. Otherwise, I will see you all on Wednesday. Have a nice day. Bye-bye. All right, I'm gonna put some of you in a waiting room and I'll grab you one at a time. Hey, Kayla, just you and me. How are you?
I'm good. You?
Good.
Do you have some time today that we could go over just a few things?
Yeah. How much time do you need?
I don't want to make them wait for a while, so just whenever you have maybe like 10 or 15 minutes.
Okay, yeah, why don't, let me put you back in the waiting room and I'll bring them in. I think they have all relatively quick questions.
Okay.
Okay, and then we can
All right,
just, we can get it done now. Okay. Hey, Megan, do you have a question? Megan? Okay. If you